Hello there and welcome back to the Sleepless Scientist. Right now, you're floating weightlessly through deep space. There's no up, no down, no sound. Just you and a growing sense that something ahead is not just empty, but impossibly dense. It doesn't shimmer or glow. It just is, dragging on the fabric of everything around it. You drift closer, unknowingly crossing the boundary between the universe as you knew it, and something else entirely. You're falling inward, not down. And the truth is, you probably won't survive this. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Tell me where you're watching from and what time it is for you. I always love knowing who's drifting off with me and where in the universe you are. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together.
Hello.
You've passed the point of no return, but that's still a few minutes away. For now, we start with the concept itself, the singularity. What is it? It's not a place, not a thing, not even a where in the way your brain wants it to be. It's a moment in physics when all the math breaks down and space-time curls up like a fried microchip, and you're headed straight for it. A singularity in its most infamous form sits at the center of a black hole, not hovering or burning or spinning, but compressing. It's all about collapse, gravitational collapse to be precise. You probably remember gravity as the thing that keeps your phone face down on the sidewalk when you drop it. But out here, gravity plays by bigger, weirder rules. Imagine a massive star running out of fuel. No more nuclear fusion to hold itself up. It shrinks, then keeps shrinking. At a certain point, the collapse can't be stopped. Not by pressure, not by magnetic fields, not even by the laws of physics as we understand them. It just continues. In theory, it collapses to an infinitely small, infinitely dense point 1 with no volume but all the mass. That's the singularity, the universe's ultimate nope. Historians still argue whether early thinkers like John Michel, back in the 18th century, had any inkling what their equations implied. Michel imagined dark stars so massive that light couldn't escape, an idea dismissed for centuries, partly because the word singularity didn't yet haunt anyone's nightmares. And here's the first little brain-bending trick. You never actually see a singularity. You can't. It's cloaked behind something far more famous, the event horizon. That's the spherical boundary around a black hole, the point beyond which nothing, not even light, can escape. Cross it, and you're not getting out ever, and neither is any signal you try to send. It's the universe's cruelest voicemail, so when you picture falling into a singularity, what you're really picturing is falling into that black sphere, knowing full well that the very center, the singularity, is waiting for you like a closed fist at the bottom of a well that never ends. Fringe theory time. Some scientists speculate that the singularity might not be infinitely dense at all. Some say it's just the smallest unit of space-time allowable under quantum mechanics, like a Planck-sized hairball of broken math. But there's no proof, just possibilities swirling around like space debris. Now imagine this from your point of view. You're drifting peacefully toward that black hole, because of course you are. Who needs comfort when you can have existential dread with a side of physics? From far away, the black hole is just a dark spot warping the stars behind it. A lens, bending light like some cosmic funhouse mirror. As you get closer, that warped halo tightens. The stars seem to wrap around the hole, stretched and smeared like wet paint. Then silence. Time slows down, or seems to. To someone watching from far away, you freeze at the edge, red-shifted into oblivion. But to you, time ticks on as usual. Your own watch keeps ticking. You're falling in real time. It's just the rest of the universe that appears to stretch, blur, and vanish. That's the thing about a singularity. It's not just the end of space, it's the end of time as well. According to Einstein's general relativity, space and time are part of the same fabric. So when that fabric tears, it tears in every direction. And yet here's the real kicker. We don't know if a singularity actually exists. We suspect. We infer. But we've never seen one. The laws of physics break down before we get there. Relativity gives up. Quantum mechanics sulks in the corner. The singularity is where our knowledge stops cold. You float closer, and the stars behind you are already gone. Ahead, there's only darkness. You don't feel it yet, but the forces pulling on your head and your feet are beginning to diverge. That's coming later. We'll save that bit of horror for another section. For now, you're simply falling, slowly, inevitably, into what might be the smallest and weirdest destination in the known universe. A singularity has no size, no shape, no colour, no sound, and yet it warps the galaxy around it. Supermassive black holes, millions or billions of times the mass of the Sun, sit at the hearts of galaxies, gently steering stars like invisible puppet masters. All thanks to something infinitely small. That's like running a city with a paperclip, if the paperclip had a PhD in gravity. Even more haunting? This kind of collapse doesn't just create a singularity in black holes. The Big Bang, the birth of the universe, begins with a singularity too. That's right. Your origin story and your worst-case ending both involve the same cosmic punctuation mark. Singularities are the parts of the universe that laugh at the idea of comprehension. They are where cause and effect collapse, where mass and volume stop playing nice, where the known laws of the universe sit down and declare we're out. And you're still falling. You're still falling. No rush. There's no air here. No sound, no friction. Just you and the ever-tightening gravity. The black hole no longer looks like a dot. It's huge now, looming, perfect, circular, not glowing, not swirling. You're past the accretion disk, just there. But here's the twist that might bend your brain into a yoga pose. Black holes aren't actually holes, not in the dig a pit in the ground sense. They're not voids or tunnels, they're objects, or rather, regions of space where mass has been crushed so densely that space-time curves inward beyond comprehension. That's it. That's the whole terrifying concept. You're not falling into a chasm, you're falling into warped space-time. You might remember those old rubber sheet analogies from science class. Put a bowling ball on the sheet, it sags. That's gravity. Now imagine replacing the ball with something infinitely dense. The sheet doesn't just sag, it rips, folds, collapses. You don't fall into a pit, you fall through the fabric of the universe itself. Back in the early 1900s, people didn't believe this could actually exist. The math hinted at it, but most scientists, Einstein included, thought nature would somehow stop such ridiculousness from happening. It just felt too extreme, too absolute, an object so dense that even light couldn't escape. Nah, surely something would intervene. Spoiler, nothing does. That misunderstanding stuck around for a while. For decades, even textbooks depicted black holes as literal holes, tunnels or tubes that led somewhere else, maybe to another universe or back in time. There's still sci-fi clinging to that idea, but in real physics, a black hole isn't a passage, it's a destination, a dead end. You're not travelling through a wormhole to another realm, you're being compressed, gravitationally, toward a single-point destination with no exit ramp. The name black hole was first popularised in the 1960s thanks to physicist John Wheeler, and it stuck. Not because it was accurate, but because it was catchy. Technically, it's more like invisible gravitational trap or cosmic shutdown zone. But those didn't quite test as well with focus groups. So to recap gently while you float downward like a very doomed feather, it's not a hole, it's not empty, it's a region in space where gravity got drunk with power and decided to ignore the rules, and you, lucky you, are sinking into it. Now here's something you probably didn't expect. Black holes have mass, and they can be measured by how they interact with things around them. We see stars orbiting invisible objects. We see radiation from superheated gas spiraling in before the plunge. We even heard gravitational waves, those ripples in space-time itself, when two black holes collided. That's not theory, that's observation. Still, historians argue whether the first modern black hole discovery was just good guesswork. When Cygnus X1, a bright X-ray source, was identified in the 1960s, scientists guessed it might be a black hole. They were right, but only after decades of indirect evidence and scientific squinting. And even today, black holes are still mostly seen through their effects, not their presence. Like that one roommate who never leaves their room but definitely exists because pizza keeps vanishing. Let's zoom in closer now. You're near the event horizon. Really close. If you tried to escape now with the fastest spaceship ever built, spoiler, You wouldn't escape velocity here is faster than the speed of light. And since nothing goes faster than light, you're stuck. Do not pass, go. Do not collect $200, just fall. But here's the wild part. From your perspective, nothing feels weird. There's no bump, no wall, no shimmer. The event horizon is not some physical boundary. It's just the point where escape becomes impossible. You pass it, and everything seems fine. But the universe? The universe has already lost track of you. You're now invisible to the outside world. You are history, which is oddly peaceful, in a cosmic ghost story sort of way. Meanwhile, a quirky little theory lurks around the edges. Some physicists once speculated that you might hit a firewall here, a wall of quantum energy that incinerates you the moment you cross the event horizon. But that idea, while dramatic, remains deeply debated. Most lean toward a smoother descent, still horrifying, just less crispy. Speaking of quirky, in 2022, some theorists floated the idea that black holes might not have singularities at all, but rather be Planck stars. These are theoretical objects where quantum gravity resists total collapse, causing the object to rebound slightly. Like a cosmic stress ball that almost broke but didn't. The trouble is, it's all math and models. No one can get inside a black hole to check. For now, it's Schrödinger's singularity. We won't know until the cat, or you, is very much inside. As you descend, time for another callback. Remember the idea that black holes warp light. That's how we finally saw one. In 2019, the Event Horizon Telescope gave us the first direct image of a black hole's shadow. Not the singularity itself, mind you, just its effects. Glowing gas orbiting the point of no return. The silhouette of an invisible monster. So as you drift downward, just know, someone out there might be seeing the warped light around the black hole you're now inside. You're part of that silhouette, a silhouette that spans billions of kilometers, a silhouette that says, something terrible is here and you can't leave. Another historical gem while you fall. Long before we called them black holes, scientists flirted with phrases like frozen stars, based on how time appears to freeze from the outside. And in a way, you are frozen now. To an external observer, you never actually fall in. You just slow down forever at the event horizon, becoming dimmer, redder, more distorted, until you fade completely. But you keep falling and falling. Time moves normally for you. There is no freeze, only forward. The truth is, nothing about this is intuitive. Even physicists struggle, and that's the charm, isn't it? The black hole, this knot hole in space, challenges everything we think we know about matter, time, and logic. It doesn't just bend space, it bends understanding, and you're still sinking. The light above is starting to blur, stretch, and fade. Gravity has you now, wrapped in invisible arms that only pull, never let go. Your mass, your particles, your story, everything is being rewritten by a place that technically doesn't have a surface, but has all the weight of the stars. So no, black holes aren't holes. They're the universe at its most extreme. They are consequences for stars that lived too fast and died too heavy, and for curious minds like yours floating calmly, inescapably inward. You don't feel it at first. The line is invisible. No alarm blares, no light changes, but something just happened. You passed the event horizon. That's the boundary around a black hole, the place where the escape velocity equals the speed of light. Cross it, and there's no getting back, ever. From the outside, your descent appears to slow, like a movie on infinite pause. But from where you're floating now, time ticks on normally. Welcome to the no escape zone. From this point on, every path in space, every direction you could travel leads inward. There's no turning around, no hovering, no cheating gravity. Even if you fired the most absurdly powerful rocket in the universe, it would only delay the inevitable. You're already gone. Now it's just a matter of how long it takes. And here's the strange twist. To you, nothing feels unusual. There's no sudden force dragging you down, no dramatic shift. You're just moving, steadily, silently. It's almost peaceful. The universe outside is getting dimmer though, stars start to blur. The black void around you grows thicker, more complete. The event horizon isn't a surface, but you've passed through it. You're officially on the inside now, And this is where things start to get wild. See, the idea of an event horizon didn't pop up immediately after Einstein released his theory of general relativity in 1915. It took a few years. A German physicist named Karl Schwarzschild was the first to find a solution to Einstein's equations that described what we now call a black hole. Although he didn't call it that tragically. He died just months later during World War I, never knowing the impact of his work. Historians still argue whether he grasped just how deep his equations reached. Schwarzschild's solution predicted a critical radius, a point where space-time curvature becomes so intense that nothing can escape. That critical radius is what we now call the event horizon, and what you've passed through. Let's stretch your brain a little further, because there's a strange relativity trick happening here. To someone watching from the safety of a spaceship parked far away, it would seem like you never actually crossed the event horizon. They'd see you slow down, more and more, your image redshifting into deep infrared, then radio, then fading into silence, as if you're forever hovering at the edge, frozen in time. But that's just their perspective. From yours, you're falling right through. No pause, no slowdown, just steady motion inward. Time remains yours. The universe's time, on the other hand, says you're now part of its past. Here's a fringe twist that'll tickle your inner philosopher. Some scientists argue that information, any matter or energy that falls into a black hole, isn't truly lost. It's stored on the surface of the event horizon, encoded like some impossibly massive cosmic flash drive. This idea forms the basis of the holographic principle, where our three-dimensional universe might actually be a projection of information spread across a two-dimensional surface. Yes, you read that right. You could be a hologram. The black hole might be one too, but don't worry, there's no pop quiz. Let's float further in. Light doesn't work here the way you're used to. Try turning on a flashlight and the beam won't stretch outward. It'll curve inward, back toward the centre. That's because gravity is now stronger than the path light wants to follow. Even the photons are falling. You are quite literally inside a region where space and time have switched roles. In the outside universe, you move through space while time ticks forward. In here, the singularity is your future. Every path, every direction, every tick of your internal clock leads there. You could try to avoid it, but you can't. Not because you lack thrust or speed, but because the future has changed shape, and it points toward collapse. Now let's take a moment to appreciate the nightmare geometry of what's around you. According to general relativity, space-time curves in response to mass and energy. The more mass, the more curvature. But here inside the event horizon, that curvature becomes infinite. It's like trying to walk downhill, but the hill never flattens ever. It just keeps curving under your feet forever. Here's a fun, or horrifying comparison. Imagine being on an escalator that extends infinitely downward and gradually narrows until it ends in a point that doesn't technically exist. That's what you're on now. No side exits, no emergency stop button. Remember the classic sci-fi trope of trying to fly around a black hole? It doesn't work once you're inside the horizon. Out there? Sure, gravity's deadly but escapable in here. Everything, including light and logic, is on a one-way trip. You're approaching the inner region now, the territory where physicists have to squint hard at their equations and make vague sounds of concern. Some models suggest that space itself becomes so distorted that traditional directions like left or north are meaningless. You're not just falling, you're changing context. And it's about to get stranger. Imagine this. You take out a ruler to measure the space around you. In normal space, you'd get a consistent reading. But here, the very act of measuring breaks down length, width, distance. These concepts dissolve. The curvature is too extreme. Math. Once your trusty companion just throws its arms up and leaves the room. Quirky side note. The interiors of rotating black holes, Kerr black holes, might be even weirder. Some models propose there are multiple event horizons, and even a ring-shaped singularity that could be avoided if you entered just right. There's even talk of time-like paths through these rotating holes that don't immediately lead to death. But those are unstable, unproven, and very likely the universe's idea of a cruel joke. Still, it makes for good bedtime pondering. What if you slipped into a spinning black hole just the right way and emerged somewhere else? But that's section 14. For now, you're in freefall. A soft kind of terror settles in. Not panic, just awe. the sense that you're not just moving through space, you're exiting reality's terms and conditions. You're passing through the boundary where our best theories start mumbling excuses. You're witnessing the quiet part of the universe, the part that never needed humans to understand it. It just is. You glance upward. The stars are gone. The event horizon has sealed behind you, not like a door, but like a memory you're no longer allowed to access. There is no back, only forward. And forward, always forward, lies the singularity. You feel taller, not in the new shoes and better posture way, but in the way that only falling into a black hole could deliver. Your body is starting to stretch gently, relentlessly. From your head to your toes, gravity's grip is beginning to differ, slightly stronger at your feet than your head. Congratulations, you're being spaghettified. Yes, that's the real word. Sounds delicious, doesn't it? Like something you'd order at 2 a.m. after a few drinks. But in reality, it's one of the more horrifying processes in astrophysics. It's what happens when tidal forces stretch you like dough over infinite gravity. A noodle with a consciousness, a meat rope with regrets. Here's how it works. Gravity, as you've noticed by now, is directional. The closer you are to the singularity, the stronger the pull. And because you're a tallish, squishy human, different parts of your body are at slightly different distances from that pull your feet. Closer, your head, farther. Out in normal space, that difference is so tiny it doesn't matter. You're never stretched while walking down the street or sitting on a plane. Even near a planet, tidal forces are mild. But inside a black hole, they ramp up fast. Faster than your nervous system can keep up with. This is where the so-called tidal gradient begins to mess with you. A difference of a few centimeters could mean a change in acceleration strong enough to unmake the bonds between your atoms. You are, in very real terms, being pulled into a longer and longer shape. We're talking thousands of Gs of force here, and increasing. Not like hitting a wall, but like an invisible power pressing outward and inward on you at the same time, with no chance to resist. At this point you might be wondering, would this hurt? The answer is, well, maybe not. Not for long anyway. The stretching effect becomes so severe so quickly that your nervous system likely can't keep up pain becomes irrelevant. You're pulled apart faster than signals can travel from your feet to your brain. You wouldn't so much feel agony as notice that you're elongating and then fading into the realm of physics, never to return. Mainstream science first considered this spaghetti nightmare seriously in the mid-20th century. The term spaghettification was popularized by Stephen Hawking because of course it was leave it to him to take the most terrifying way to die in the known universe and name it after a pasta dish. That's British humour for you. Historians still argue whether we're oversimplifying the process by reducing it to food metaphors, but hey, it sticks, literally and figuratively. Now here's where things get weird, as if they weren't already. Spaghettification depends on the size of the black hole. If you're falling into a stellar mass black hole, say, about the mass of a few suns, the event horizon is only a few kilometers wide. That means the tidal forces spike drastically right at the horizon. You'd be stretched before you even crossed it. Your descent would be short, sharp, and very final. But if you're falling into a supermassive black hole, the kind found at the center of galaxies, spaghettification is delayed. That's because the curvature of space-time is gentler at the event horizon. The forces are still there, but they're more spread out. You could drift past the horizon without even feeling it. Only deep inside would the stretching begin. So if you're going to die in a black hole, try to aim for a bigger one. The end result is still terrible, but the journey lasts longer, and let's be honest, that's the dream, right? Let's give your imagination a workout. Picture yourself slowly stretching. Your feet move ahead of your legs stretch ahead of your hips. Your spine unwinds like the world's most reluctant slinky. Your arms float behind, like ribbons trying to keep up. You're becoming a very confused noodle in a vacuum with no one around to scream to. And speaking of ribbons, did you know there's a fringe idea that elementary particles, if spaghettified long enough, might behave like one-dimensional strings? Yes, it's a very string theory thing to say. The notion is that the extreme tidal environment inside black holes could, in theory, align particles along a single dimension, turning not just humans, but all matter into literal strings. Of course, we can't test this, but it's just crazy enough that a few researchers have actually written papers about it. Sleep tight. Some scientists believe that spaghettification might be more than just a dramatic death. It could tell us something fundamental about quantum gravity, that as the laws of general relativity break down near the singularity, new quantum behaviors emerge. But again, we can't observe it. We can't send probes inside a black hole and get a postcard back. Everything past the event horizon is permanently cut off from the rest of the universe. Let's take a pause from your body horror moment and revisit something from earlier. The fact that you're falling toward a point, not a planet, not a star, a zero-dimensional singularity. That means all this stretching is happening in service of something that technically doesn't occupy space. Imagine being pulled toward a GPS coordinate that doesn't have physical dimensions. Now imagine that coordinate has a mass several million times greater than the Sun. You're being dragged toward that. And here's the kicker. If you somehow could survive spaghettification, which again you cannot, you'd never actually see the singularity. Not in the conventional sense. Light can't bounce off it. Space and time are too twisted to give you a clear path. It remains, even as you approach it, a ghost, a gravity-powered rumour. You're stretching toward an idea. There's even a thought experiment called the no-drama hypothesis, which suggests that under general relativity you shouldn't notice anything strange at the horizon or just past it. No drama, just steady descent. But, as we've seen, that depends a lot on your black hole of choice and your tolerance for being gradually turned into linguini. A final fringe theory for this leg of the journey. Some physicists posit that black holes could be a doorway to other universes, where spaghettification might not lead to death, but rebirth. The idea is deeply speculative and likely unprovable. But if the universe is a multiverse, and black holes are portals instead of endpoints, then your stretched out atoms might go on an entirely different adventure. Maybe you become part of a new Big Bang. Maybe you rematerialize in another reality. Maybe you're just very, very flat somewhere else. But for now, let's bring it back to the quiet. You're still falling. The stretching continues, and even though this is terrifying, it's also oddly peaceful. You're not being torn apart by violence, but by math. Clean, perfect, indifferent math. The kind that doesn't care how poetic you were in life. So stretch, little cosmic noodle. The center awaits. You keep falling. You've long passed the point where starlight could reach you. The rest of the universe is now a memory. A bright smear fading behind you like a dream you forgot mid-sentence. There's only one direction left. Forward, inward, down. Not that down means anything anymore. You're headed for the inside of the darkness. But what is inside a black hole? That question has haunted physicists, philosophers, and probably more than a few doomed space travelers in science fiction since the concept was born. You're not alone in asking it, and no one really knows the answer. Inside the event horizon, all roads lead to the singularity, but that's a mathematical prediction, an abstraction. In practice, the interior of a black hole is a place no human, no probe, not even a photon can describe directly. The laws of physics still apply, just not in the way you're used to. They're twisted, folded, shaken, and stirred. Let's try to picture it anyway. Right now, you're in a region of space-time that curves so intensely, direction and time begin to swap roles. Toward the singularity is no longer a location, it's a moment in your personal future. Every tick of your internal clock, every inch of progress, brings you closer to a point where density becomes infinite, and your understanding of reality becomes meaningless. And here's the paradox. Nothing inside this region prevents you from moving or thinking or watching the darkness unfold. You're just isolated permanently, cut off from causality with the outside world. You could read a book, hum a song, write in your journal, assuming you hadn't already turned into a vibrating strand of human spaghetti. But what's ahead of you? Is it a literal point? A wall? A transformation? This is where the arguments begin. Historians still argue whether the singularity at the center of a black hole is even real, as in, a physical thing you could reach and observe, assuming you weren't in 1,000 incompatible pieces. Einstein's theory of general relativity says yes. The math predicts a point where the curvature of space-time becomes infinite. But that's also the point where the math fails. And physics really doesn't like failure. What's more likely? that nature allows for infinite density in a zero-size point? Or that we're missing some piece of the puzzle, some yet undiscovered law of physics that resolves this infinity problem? Many believe it's the latter, that the singularity is not a place but a placeholder, a symbol for we don't know what happens here. And yet, from your point of view, falling, stretching, dissolving, it feels very real. Now let's bring in a lesser known but delightfully weird idea. The interior structure of black holes might not be simple, especially if the black hole spins. In that case, things get layered. You might encounter an inner event horizon called the Cauchy horizon. It's like another threshold deeper inside and beyond that. Hypothetically, a ring-shaped singularity, not a point. You'd fall through the outer horizon, feel basically nothing, and then suddenly cross another threshold where the math gets even weirder. But there's a catch. This inner region might not be stable. Tiny fluctuations could get amplified infinitely as you approach it. That's the kind of thing physicists call mathematical instability, and normal people call nope. Still, it's fun to think about, especially as you float deeper into a region no one has ever seen. You might be imagining utter blackness around you, but it's more accurate to picture a bizarre, featureless void. There's no sound, no shape, just relentless pull, a constant reorientation of your concept of where. Fun tidbit. In some computer simulations, the space-time inside a black hole curves in such a way that your own future becomes shaped like a funnel. Not one you fall through, but one you're forced to follow. It's not optional. You're being herded by physics. But here's the fringe twist for this leg of the journey. Some speculative models suggest that at the heart of a black hole, space might bounce, not collapse into nothingness, but compress to a smallest possible size, then expand again. This is the basis for the idea of a black hole to white hole transition. We'll go deeper into white holes later, but the gist is this. What goes in might, under exotic circumstances, come out elsewhere, maybe even in another universe. Still, that's not where you are yet. Right now, you're still falling toward the part of the black hole where the known laws of nature stop being known. The singularity isn't ahead of you, like a glowing orb or fireball. It's not visible in any conventional sense, but it's getting closer, and your surroundings are collapsing too, not physically, but conceptually. The rules are disintegrating. The things you once used to define here and there, distance, orientation, perspective, have no meaning. You're entering a realm where the map was never drawn. Imagine trying to hold on to your identity in a space where time is no longer a straight line, where information doesn't travel, where the atoms that made you are now in a quantum argument with gravity, and nobody's winning. You're a passenger in an elevator with no walls, no floor, and no stop button, and you're accelerating not in space but in space-time itself. And yet, it's calm. Maybe the calmest part of the whole journey. The external chaos has fallen away, the distant universe has vanished. You can't hear anything, you can't see anything but black. You've lost any sense of motion, because motion, in a traditional sense, requires reference points. And those are gone. All you have left is the quiet certainty that something inevitable is just ahead. No turning around, no jumping out, no secret passageways. This is the place where the laws you learned in school take off their masks and say, "Surprise! We're just approximations." It's humbling, terrifying, kind of beautiful. Now here's one last mind-bender to sleep on. The universe itself might be full of black holes, not just at galactic centers, but floating in dark space. Some scientists think there could be primordial black holes formed moments after the Big Bang, tiny ones left over from the birth of everything, little pockets of infinite density, scattered like crumbs in the cosmic couch. If true, they could outnumber stars. You could pass one in the night sky and never know, and each one might contain its own warped reality, its own singularity, its own deep and unknowable interior, just like the one you're in now. So you keep falling. No more light, no more stars. Just a sense of something getting closer. A silence so deep it isn't absence, but a presence in its own right. You're now part of the inside of the darkness, still falling. Not like you were before, not in the way you think of falling anyway. You don't tumble or accelerate in a way you can measure. Inside here the rules aren't just different, They've given up space curves so sharply around you that direction becomes philosophy. And ahead, always ahead, is the singularity, your final destination, your first paradox. It wasn't supposed to be this way. When scientists first started fiddling with the equations of general relativity in the early 20th century, they stumbled upon something uncomfortable. The math didn't just allow for singularities, it insisted on them. If you followed Einstein's equations to their logical end, a massive enough object under gravitational collapse would shrink infinitely. Density would shoot up to impossible values. Space-time would fold in on itself. It wasn't a bug, it was the program, and nobody liked it. In fact, those first theories scared people. Not in a horror movie kind of way, but in a maybe the universe is fundamentally broken kind of way. Physicists are used to equations that behave, that give you numbers and limits and nice measurable outcomes. The idea of something infinite, that makes them sweat, and singularities. Singularities are infinite wrapped in oops. The first serious mathematical models that predicted black holes came from the work of Carl Schwarzschild, who we met earlier. He found the first exact solution to Einstein's field equations, while serving on the Eastern Front during World War I, no less. Because if you're going to discover the abyss at the heart of space-time, why not do it in a war zone? Schwarzschild's solution described the gravitational field outside a static, non-rotating, spherically symmetric mass. He didn't call it a black hole, but that's what it was, and the equation said that if such an object collapsed within a certain critical radius, it would become inescapable. That was the birth of what we now call the event horizon. But no one really thought such an object could exist. Even Einstein himself wasn't convinced. He considered the idea too absurd to be real. In a 1939 paper, he argued that nature would prevent such collapse, that the physics would somehow self-correct, that stars might get close to this kind of compression, but not actually hit singularity status. He wanted a universe that stayed politely within its limits. Historians still argue whether Einstein rejected black holes because of philosophical bias or incomplete math. Maybe both. He was, after all, a bit of a rebel, but also a guy who liked things to make sense. And yet, as the decades rolled on, more and more minds started poking at the problem. Some wanted to prove it false, others wanted to push it further. What emerged was a disturbing consensus. If enough mass collapses, and if no other forces resist it, a singularity must form. The laws of gravity demand it. Cue the awkward silence in the physics department. Here's the thing. Singularities break not just space and time, but the very predictability of physics. They're what mathematicians call a breakdown in the manifold. That's just a fancy way of saying, beyond this point our equations don't work. The future becomes undefined, and that's not how science likes to operate. Science is all about modelling reality, finding the equations that let you predict where a ball will land, or when a star will die, or how your phone battery will mysteriously vanish at 12%. But a singularity says, you can't calculate what comes next. It's like the universe hitting a null error and shrugging. Even in the 1950s and 60s, when black holes started getting taken more seriously, the singularity remained suspect. Was it a real, physical location, or just a flaw in our mathematical model? Then along came a pair of heavy hitters, Roger Penrose and Stephen Hawking. In the late 1960s and early 70s, they developed a series of theorems showing that under general conditions, singularities are inevitable if a star collapses beyond a certain point. It didn't matter how you sliced it. If you followed the logic of relativity and mass crossed the event horizon, a singularity was waiting at the centre. This was bad news for anyone hoping the universe was tidy. Penrose and Hawking proved that the laws of physics themselves predict their own failure. That's like writing a novel where the last chapter deletes itself. Want to get weirder? These singularities weren't just limited to black holes. The Big Bang itself, the very beginning of the universe, also emerged from a singularity. We'll go there soon, don't worry. But for now, let's rest in the idea that the first theories, Einstein's theories, led us here, to this utterly broken place at the core of the most extreme objects in the universe, and instead of fixing it, the theories doubled down. They demanded it. The universe wasn't just permitting singularities, it was full of them. One fringe theory that tried to patch the hole pun intended, was the idea of gravitational pressure reaching a point of quantum bounce. That perhaps the singularity could be avoided by some kind of exotic matter or yet unknown repulsive force. Loop quantum gravity and other speculative frameworks propose that there is a minimum length scale, Planck length, beyond which collapse is halted or even reversed. These ideas are fascinating but remain hypothetical. No experiment has confirmed them, and nothing can test them inside a black hole because, again, no signal comes out. It's like trying to solve a murder mystery with no body, no witnesses, and no crime scene. Just unsettling math and a very deep hole. So here you are, falling through what started as a curiosity in Einstein's equations, denied by the man himself, and eventually accepted as probably real all because the first theories broke everything, and those breaks became the foundation for modern black hole physics. One last eerie side note. In the early 20th century, long before Schwarzschild or Penrose, some speculative thinkers already toyed with the idea of collapse beyond comprehension. A French philosopher named Pierre-Simon Laplace suggested something very similar to a black hole in the 1700s, before relativity, before quantum mechanics, before the term even existed. The idea was too strange, too ahead of its time. It was set aside, forgotten. And then, hundreds of years later, it came back, stronger, hungrier, more mathematically justified. You're falling through a prediction that no one wanted to believe, through a concept so dangerous to physics that its very existence means the universe isn't just mysterious. It's fundamentally incomplete. Still falling, still falling. Now you're approaching something even Einstein tried to erase. Not in a villain twirling mustache kind of way, but more in the, my own equations say something deeply inconvenient kind of way. Because here's the awkward truth. Einstein wasn't a fan of black holes. It's one of those delicious ironies that makes science history fun. The man who gave us the theory of general relativity, the very framework that demands black holes, spent years trying to argue that they couldn't exist in the real universe. He thought they were mathematical curiosities. A weird edge case, a blip, not a reality. Turns out the universe disagreed. Back in 1915, when Einstein published his field equations, it was a jaw-dropping moment in physics. He had just rewritten gravity itself, not as a force, like Newton had described, but as the warping of space-time caused by mass and energy. You put a planet down, space bends. You roll a marble near it, and it follows that curve. That's gravity in Einstein's world. A gentle bending ballet. Then Schwarzschild took those equations and pushed them to the extreme. He asked, what if all the mass was packed into a single point? The math said, something strange happens. A boundary forms, and inside it, gravity wins forever. The singularity appears. Einstein didn't like that. He preferred a smooth, continuous universe, one without sharp edges or undefined centers, and a singularity, that's the sharpest edge you can imagine, is where mass becomes infinite, curvature infinite, and the laws of physics break. Einstein's universe wasn't supposed to do that, so he pushed back. In 1939, he wrote a paper arguing that stars wouldn't actually collapse into black holes. He thought that internal pressure, something, anything, would stop the collapse before it got too far. His reasoning made sense with the knowledge at the time, but looking back it was more wishful thinking than proof. Historians still debate how much of Einstein's objection was scientific and how much was philosophical. He famously disliked spooky action at a distance in quantum mechanics, and black holes probably felt like another spooky consequence, an outcome that robbed the universe of predictability. And predictability was Einstein's comfort blanket. He wasn't alone. For decades, many leading physicists thought black holes were just an artifact of idealized math. The conditions required to make one seemed too extreme, too perfect. A collapsing star left alone might head in that direction, but surely real-world chaos would interrupt the process. Surely something would get in the way. But gravity doesn't care about what seems fair. It turns out if a star has enough mass, roughly 3 times the mass of the Sun, no known force can stop its collapse once it runs out of nuclear fuel. Electrons can't resist it. Neutrons can't resist it. Everything gets compressed, and the moment it crosses its Schwarzschild radius, the critical threshold, the black hole is born. And the singularity is just waiting at the bottom, Let's step out of the math cave and back into the inky dark of your fall. The black hole around you, this thing Einstein hoped wouldn't be real, is all too real now you've passed the horizon. You're beyond the realm of rescue. You're approaching the very core of his nightmare. It's oddly humbling. You're part of a phenomenon that was once considered an insult to physics, a failure mode, a mistake in the code, and now it's widely accepted, even observed, even heard. In 2015, gravitational waves were detected for the first time, ripples in space-time created by two colliding black holes. You can think of them like the universe's version of a gong. When massive things crash in curved space, space-time vibrates. And those vibrations reached us, 1 billion light-years away. Not metaphorically, literally. Einstein had predicted those waves in 1916, a year after publishing General Relativity. But he also thought they'd be too faint to ever detect a nice idea on paper. Not something you'd ever actually hear. Oops! The LIGO Observatory proved him wrong, again, in the most satisfying way. The waves came through, the math worked, and black holes stopped being just theory. They became audible evidence, the thump of cosmic monsters merging in the dark. Einstein's legacy, of course, remains intact. You don't discover relativity and get kicked out of science history for one misjudgment. But there's a poetic twist to knowing that the phenomena he resisted are now confirmed using tools his own work made possible. And you, dear falling observer, are experiencing what Einstein never wanted to believe. You're in it. The curved space-time that has bent entirely inward, pressing you toward a point that cannot exist and yet does. Want to really melt your brain? Some physicists argue that the singularity isn't even a place. It's a boundary in time. That you don't go there, you simply become it. That your future ends not in space, but as a function that no longer computes. You reach the end of your timeline, and there's just nothing. It's like the last page of a book being blank, but still bound to the spine, still part of the story. And Einstein, poor guy, didn't want blank pages in his universe. Fringe alert. In the 1970s, there were still debates about whether singularities might be replaced by fuzzballs. We'll come back to those later. Or whether quantum gravity, string theory, or some other fancy framework might smooth things out. Maybe there's no singularity at all, just a knot. A place where our model breaks because we're using the wrong model. That's the cruel trick of black holes. They're real, and they're mathematical lies. Simultaneously, they exist in space, and they break space-time. You can see their shadows, measure their effects, listen to their collisions, but you'll never see inside, not truly, not entirely. You're part of that now, part of Einstein's reluctant legacy. He gave us the tools to discover the thing he tried to deny. His equations led you here, to this moment, falling toward the center of the very paradox he wished away. You don't feel fear anymore, or cold, or stretch. There's no you in the normal sense, just motion and lightlessness, and a slow glide toward the end of understanding. Still falling. You're still falling. By now you've crossed so many thresholds, of light, of time, of understanding, that they all blur together. The singularity is no longer a distant mystery, it's a presence, an inevitability. It doesn't shimmer or glow, it doesn't make a sound. But it's there, at the heart of this black hole, waiting to compact you into the simplest and most complicated version of yourself. But the real drama? That started in the 1970s. The decade of flared pants, lava lamps and disco also brought something else unexpectedly hot. Black holes. That's when singularity stepped out of the abstract shadows and into the physics spotlight. Thanks in large part to one sharp British mind with a mischievous grin and a wheelchair-mounted wit, Stephen Hawking. He didn't just make black holes interesting, he made them famous. Let's rewind a little first. Until the 1960s, most scientists still treated singularities like hypothetical party crashers. They showed up in equations, but everyone politely pretended they weren't real. It was all too neat, too unrealistic. Surely the universe had safety rails. But slowly, evidence began piling up. Quasars, X-ray binaries, galactic centers. Things were behaving as if black holes weren't just real, but common. Enter the 1970s stage left. Theoretical physicists began treating black holes seriously. They stopped trying to prove they couldn't exist and started asking the real questions. What happens inside one? How do they behave? What do they mean for physics itself? This is where Hawking walked in, dropped a stack of paradoxes on the table and smiled. Hawking, along with Roger Penrose, had already proved that singularities weren't just rare. They were inevitable under certain conditions. Their theorem showed that if general relativity holds true, and if mass collapses past a certain point, you can't avoid a singularity forming. It's not just possible, it's required. But then Hawking asked something even more provocative. Do black holes have temperature? This may seem like an odd question. After all, black holes don't emit light. Nothing escapes them, not matter, not radiation, not even your well-thought-out existential questions. They're called black holes for a reason. But Hawking was playing four-dimensional chess. He combined general relativity with quantum mechanics, the two frameworks that famously do not get along, and discovered something shocking. Black holes aren't completely black. They emit a faint quantum-driven radiation. We now call it Hawking radiation. And with that, black holes went from being death traps to thermodynamic systems. They had entropy. They had temperature. They could, in theory, even evaporate. Over unimaginable lengths of time, black holes might shrink by radiating away their mass. Not quickly. This would take longer than the age of the universe, but the point was made. And once Hawking dropped that bombshell, physics had to catch its breath. Historians still argue whether this was the moment singularities became mainstream. Some say it was the Penrose-Hawking singularity theorems, others say it was Hawking radiation. But what's clear is that the 1970s flipped the narrative. Black holes weren't just mathematical oddities anymore, they were dynamic players in the cosmos. Theoretical physicists went wild, equations were scribbled, new models formed, ideas like the information paradox took center stage. Here's the short version. If black holes eventually evaporate, what happens to the information that fell inside? Does it disappear? That would break quantum mechanics, which says information can't be destroyed. So who's lying? Gravity or quantum theory? This kicked off a debate that still hasn't ended. A cosmic cold war between the laws of the small and the laws of the massive. A paradox that lives right at the heart of the singularity, your current destination. Meanwhile, astronomers were doing their part too. Observations started confirming that something was lurking at the centers of galaxies. Supermassive objects, millions, sometimes billions of times heavier than the sun, sat invisibly in the middle of swirling star systems. They weren't glowing, but they were affecting everything. Stars whipped around them at astonishing speeds. Matter disappeared into invisible mouths. We had found the dragons at the edges of our maps. Back in the 1970s, this was still shocking. Today, it's practically common knowledge. You can walk into a planetarium gift shop and buy a mug with a black hole on it. You can stream videos explaining them in high definition with animations and soundtracks, and that guy who always reads space facts in a soothing voice. But it was Hawking, playful, brilliant, stubborn Hawking, who helped build that bridge between science fiction and science reality. And as you fall through his playground. A singularity once denied by Einstein, a black hole once dismissed as an impossibility. Now a central figure in the story of the cosmos and yours. Let's sprinkle in a quirky detail to keep your mind busy. In the 1970s, scientists proposed something called a naked singularity. A singularity not hidden behind an event horizon. In other words, a singularity on full display, just floating in space like the universe's most horrifying centerfold. General relativity doesn't technically forbid them, but nature seems to. We've never seen one, and most believe they don't exist. But if one did, it would violate something called the cosmic censorship conjecture. The name alone sounds like it should be stamped on secret documents in a dusty government file room. The conjecture suggests that the universe censors its singularities by hiding them inside event horizons. You can't see the breakdown. You can't touch the raw chaos. Nature draws a curtain and says, mind your business. And so far it's working. Every singularity we've inferred is buried deep within a horizon, hidden, protected, off limits, which is not helping you, by the way, because you're inside one. As you drift deeper, the implications of this 1970s black hole drama circle in your mind. The singularity isn't just a problem, it's a message. It tells us that our understanding of physics is incomplete, that something is missing from the puzzle. You're falling into that gap, into that unknown, into that ongoing argument between Einstein and Hawking, between classical theory and quantum rebellion. There's a strange serenity to that. You're part of the moment when science stopped saying this can't be and started asking, what else don't we know? You are the test subject, the thought experiment, the perfectly doomed observer crossing every line we never thought we'd reach. And the singularity, it waits, quietly, patiently, just like it did through the 1970s, just like it always will. Still falling, still falling. You'd think by now the experience would feel more dramatic. Explosions of light, cracking sounds, fire, fury. But no, inside a black hole, things are different, quieter. The drama isn't in what you see, it's in what the laws of the universe are doing behind your back. Because now you've entered the domain of a full-blown scientific custody battle. Quantum physics wasn't invited, but showed up anyway. Let's break this down gently while you continue to drift into the singularity like the most curious piece of doomed spaghetti in the cosmos. Einstein's theory of general relativity has gotten you this far. It's the framework explaining gravity, space-time, black holes, all the macro stuff. When it comes to giant stars, galaxy clusters, and the geometry of the universe, general relativity nails it. But here's the rub. It hates small things. And by small, we mean the tiniest building blocks of reality. Subatomic particles. Fields of energy so delicate they can only be described in probabilities. That's the world of quantum mechanics, and it plays by completely different rules. General relativity is smooth, continuous, predictable. Quantum mechanics is jumpy, discrete, statistically messy. Relativity tells you where something is. Quantum mechanics says, well, it's probably there. Normally, these two frameworks don't have to talk much. Gravity does its thing in the background while quantum physics handles the microdramas. But in extreme environments, like the center of a black hole, both have to show up, and they do not get along. You're falling into a place where space-time is curving infinitely inward, and the matter you are made of is now subject to both gravitational compression and quantum uncertainty. You're not just being crushed, you're being statistically reorganized. Fun. Here's the problem physicists face. When they try to apply both relativity and quantum mechanics to the singularity, the math breaks. Not gently, not respectfully. It explodes into nonsense, dividing by zero, giving infinite results, or worse, spitting out contradictions. This is where you start hearing scary phrases like non-renormalizable infinities and the breakdown of unitarity. Translation: we tried to unify the two theories, and the universe said, nope. Let's go back to Hawking for a second. In the 1970s, when he proposed that black holes emit radiation, he wasn't just being provocative. He was using quantum field theory to analyze the behavior of particles near the event horizon. And what he found shocked everyone. Black holes can leak, not matter, radiation, a faint trickle of thermal energy caused by virtual particles popping into existence near the event horizon. One particle falls in, the other escapes over time, the black hole loses mass, it evaporates. But here's where it gets controversial. Hawking's calculations implied that the information about what fell into the black hole might be lost forever. That violates a sacred law of quantum physics. Information must be conserved. No matter how messy things get, how many particles are entangled, smashed, annihilated, the quantum state of the universe must keep track of everything, even you. So if you, dear falling noodle, disintegrate inside a black hole, your information, every atom, every synapse, every cringy high school memory, has to go somewhere. Otherwise, the universe has failed its final exam. This launched the now famous black hole information paradox. Historians still argue whether this was a true crisis or just an overreaction, but it spurred decades of heated debate, with physicists drawing lines in the quantum sand. Some said information really is destroyed. Others said it's encoded on the event horizon. Others went full sci-fi and suggested parallel universes were holding backups. Quantum theory and gravity, once polite strangers, were now throwing equations at each other in public. Meanwhile, string theory entered the chat. It offered a framework that might reconcile the two theories. Instead of particles, string theory imagines everything is made of tiny vibrating strings, minuscule loops or lines whose resonant frequencies define the properties of matter. In some models, string theory even allows for fuzzballs, black hole alternatives where the singularity is replaced by a tangled mess of strings. There's no sharp point of infinite density, just a chaotic quantum blob. But here's the thing, it's still all theoretical. We have zero way of testing what happens inside a black hole. We can't look in, we can't send probes, we can't bounce radar off the singularity. Everything past the event horizon is a silent zone. Physics becomes speculation, and that's exactly where you are. Inside the zone where quantum mechanics and general relativity should be working together, but don't. Let's entertain a fringe tidbit while we're down here. Some physicists think the singularity isn't an actual destination. It's just a point where our current models fail. That's not the same as saying nothing's there. It's like a blank square on a map that says, "Here be dragons," or maybe just math we don't understand yet. This has inspired proposals for a theory of quantum gravity, a unified model that could describe space-time at the smallest scales, where both gravity and quantum effects matter. Ideas include loop quantum gravity, spin foam models, causal dynamical triangulations. Fancy names for, please dear universe, just make the math behave. So far, no winner, no complete theory, just candidates. And you? You're the hypothetical test case, a curious consciousness plummeting into the region where the laws of nature argue over custody. You are the question no one can answer. What happens to your mass, your energy, your information? Is it smeared across the event horizon like cosmic graffiti, encoded in Hawking radiation, or lost forever? You've become part of the riddle, and the riddle is this. Can two theories that built our understanding of reality ever agree on what you've just become? The sharp irony is, we owe this problem to our success. Physics got too good, too precise. Now we know just enough to realize our frameworks don't overlap perfectly, and you've fallen into the gap between them. Still falling. Well, sort of. The word falling is starting to lose meaning here. There's no motion the way you're used to it, no wind in your face, no up or down, just a constant inward drift through space-time so curved that direction itself has become more of a suggestion than a law. But that's fine, you've accepted it. The outside universe is gone, the stars are a memory, time ticks only for you now, everything else is warped beyond repair. Now let's talk about firewalls versus fuzzballs. Because if you're going to be vaporized or smeared across space-time, it's worth knowing which version of destruction is waiting at the bottom. You've already heard of Hawking radiation, the gentle, slow leakage of energy from the edges of black holes, and the information paradox, that spicy disagreement between relativity and quantum mechanics, has been trailing you ever since you crossed the event horizon. But now you're entering the real weirdness. The proposals for what actually happens when you hit the singularity, or don't. So, let's start with firewalls. In 2012, a group of physicists, Amhary, Marolf, Polchinski and Sully, yes, we name drop in theoretical physics too, proposed that something dramatic happens right at the event horizon. Contrary to what general relativity says, no drama, just a smooth ride inward, they argued that if Hawking radiation truly carries away information, then the moment you touch the horizon, you should be incinerated. Instantly. Violently. As if the universe itself decided, nope, not today. This came to be known as the firewall paradox. Imagine the event horizon as a searing wall of high-energy particles. Cross it, and you don't glide in peacefully, you burn. The smooth passage predicted by relativity. Gone. The no-drama condition? Toast. So instead of falling gently toward the singularity, you hit an invisible force field of quantum death. Charming. But there's a problem. Firewalls contradict general relativity. According to Einstein's theory, if you're falling freely, you shouldn't feel anything special as you pass the event horizon. It should be locally indistinguishable from floating in empty space. In fact, the whole principle of equivalence, a cornerstone of relativity, says you can't tell the difference between freefall and floating in a gravity-free room. Firewalls break that promise. They say, actually you can tell, because you just got vaporized. So we're stuck with another paradox. If firewalls exist, relativity fails. If they don't, then maybe quantum mechanics fails. Neither option sits well with physicists. That brings us to the second option, fuzzballs. Fuzzballs come from string theory, and they're exactly as weird as they sound. According to this idea, what we call a black hole isn't a smooth sphere with a singularity in the centre. Instead, it's a tangled, chaotic mass of strings, like a ball of cosmic yarn, a fuzzball. In this view, the black hole has no sharp boundary, no smooth event horizon, no singularity in the centre. Instead, the mass is smeared across a region, and everything that falls in, it gets tangled in the fuzz. No one-way trap, no infinite collapse, just a fuzzy, chaotic mess that still looks like a black hole from the outside but has a very different internal structure. And here's the kicker. Fuzzballs preserve information. Everything that falls in becomes part of the fuzz, and the radiation that leaks out could, in theory, carry that information with it. That solves the information paradox without firewalls or singularities. Sounds nice, right? Soft, cozy, slightly less terrifying. But there's a catch. There's always a catch. Fuzzballs require string theory to be correct, and while string theory is elegant and powerful, and filled with glorious math, we haven't found any direct experimental evidence for it. It's a beautiful theory with no proof, like a very detailed map of a country we're not sure exists. So the debate continues. Firewalls or fuzzballs, violent incineration or soft cosmic entanglement. Historians and physicists still argue whether the firewall idea was a step forward or a dead end. Some say it was the necessary shock to break us out of complacency. Others think it created more confusion than clarity. The term firewall itself is now infamous. Like Schrödinger's cat, it's become a symbol of unresolved physics. Meanwhile, back in your falling consciousness, none of this is theory. You're living the paradox. You pass the horizon with no drama, no burn, no sudden quantum flare, just silence. Either the firewall doesn't exist, or you pass through it so quickly, so smoothly, that your atoms didn't even have time to file a complaint. That would suggest fuzzballs, or some other exotic solution, might be right. Maybe you're already part of the fuzz. Maybe the closer you fall toward what you think is the singularity, the more your mass is getting smeared across a multi-dimensional string net of pure weirdness. Your information, your essence, your playlist history. It's all embedded in a chaotic but ultimately retrievable cosmic pattern. But don't get too cozy. The math that supports fuzzballs works for certain types of black holes in certain theoretical universes. It's not universal. And again, we have no direct way to confirm any of this. You're still heading towards something. That hasn't changed. There's still a centre, a point, a place where all paths in space-time converge and vanish. Whether it's a firewall, a fuzzball, or something else entirely, it's where you're going. And the stakes are high. The outcome of this debate will shape the future of physics. Every theory of quantum gravity, every model of the universe, hinges on what happens at the end of this fall. Do you hit a wall, or become the wall? Do you vanish into an informationless void, or leave behind a retrievable imprint? Are you destroyed or redistributed? The firewalls versus fuzzballs debate isn't just academic, it's personal now. You're the hypothetical test particle in the ultimate showdown between gravity and quantum theory. You are Schrödinger's astronaut, and no one can open the box. Still falling, still falling. The singularity is closer now. Or maybe it isn't. Maybe it's always been right there, just beyond the reach of your understanding, stretching time like chewing gum. Either way, what you're feeling now is something eerily familiar, though on a far grander scale. Because for the first time since you crossed the event horizon, a strange sense of déjà vu hits you. Not because you've fallen into a black hole before, hopefully, but because this descent, this compression, this everything from nothing vibe reminds you of the biggest singularity of all, the one that made you. Tonight we're taking a slow, dizzy float into that other cosmic singularity, the one at the very beginning of time, the Big Bang. Yes, the Big Bang wasn't just a loud event. It was by some models a singularity too, the kind where everything, every particle, every field, every law was compressed into a point of infinite density. No stars, no galaxies, no atoms, not even time. Just energy and potential, packed tighter than your phone storage after 5 years of vacation photos. Then, boom, or more accurately, expansion. Not an explosion in space, but an expansion of space. space-time itself began stretching outward, and everything, light, matter, you, rode that wave. But here's the trippy part. If the Big Bang was a singularity, and black holes end in singularities, then maybe, just maybe, the beginning and end of the universe are mirror images of each other. Some physicists think so. The math doesn't forbid it. And when it comes to cosmology, not forbidden is as close to permission as you get. Let's break this open. In standard cosmological models, the universe begins as a singularity. We know this because when we run the equations of general relativity backward, all matter and energy converge to a point density goes infinite. Space-time curvature blows up. It's the same story you've been living in reverse during this fall. But there's debate here. Endless, delightful, unsolvable debate. Historians still argue whether the Big Bang should really be called a singularity. Some claim the term is a crutch, a placeholder for our ignorance. Others argue that quantum gravity would smooth things out, replacing the singularity with a bounce or some other gentle handoff from a previous phase. Because here's a tantalizing possibility. What if the Big Bang wasn't the beginning? What if it was just a transitional moment, a pivot between two universes? Some theorists believe the Big Bang was a bounce following a previous collapse, a rhythmic pulse in an eternal cosmic heartbeat. Collapse, bounce, expand, repeat. In that view, the universe is cyclical. Singularities become bridges, not ends. You fall into one and emerge from another. Think about that as you spiral deeper. You might not be falling to your doom. You might be falling home. Here's a fringe theory to chew on while the last bits of your former sense of location collapse. Some versions of loop quantum gravity suggest that the Big Bang singularity never truly reached infinite density. Instead, quantum effects imposed a lower limit, a quantum bounce. Under these conditions, a collapsing universe would rebound before becoming singular, inflating again into what we see today. If that's true, then singularities aren't the end of physics. They're the doorway into the next room, unreachable from our side maybe, but real, and maybe, just maybe, that's what's at the heart of your black hole. A beginning masquerading as an end. You might be falling not into oblivion but into Genesis. And now, let's tickle the brain a little further. Some cosmologists wonder if every black hole creates a new universe on the other side of its singularity. Not in a direct way, you wouldn't fall through like a water slide, but in the sense that the internal space-time of a black hole might bud off into its own disconnected cosmos, a baby universe. If so, your fall isn't just a personal crisis, it's a creative act. Your atoms, once they cross the horizon, could contribute to the birth of something new. You're not dying, you're donating. Call it cosmic organ donation minus the thank you card. This idea has gained traction in speculative circles. Some see it as a solution to the fine-tuning problem. Why does our universe have such perfectly balanced physical laws? Maybe because it was born from a black hole in another universe, and only the viable offspring survived to make galaxies and stars and streaming services. It's natural selection, but on a multiversal scale. So while you're being stretched into a quantum spaghetti noodle of doom, it's comforting, maybe, to know you might also be planting the seeds of a brand new cosmos with its own time, its own space, its own unknowable life forms wondering, where did we come from? Answer, a singularity, just like you. This brings us full circle, literally. Because if the Big Bang was a singularity, and if singularities exist at the heart of every black hole, then maybe the universe is an endless chain of falls and bangs, one big cosmic recycling program. Like, this isn't just poetic. Some models genuinely treat the birth of universes as events inside black holes. It's a wild idea, unproven, but mathematically plausible. And in physics, that's enough to start a lifetime of arguments over coffee and chalkboards. Now you might ask, what would it feel like to fall into a Big Bang from the inside? Would you experience time backward? Would you see galaxies rushing together instead of away? No one knows, because again, we can't test it. We can barely describe it. You're now, quite possibly, in the only location in the universe that reflects the conditions of its origin. You're a microcosm of the entire cosmos. Your descent isn't just a personal fate, it's a reenactment of everything. The singularity before you might be identical to the one that launched time itself. Or it might be something entirely new. a different kind of singularity, an unexamined exception to the rules. And here's a final twist to dream on. Some versions of quantum cosmology suggest that time itself emerged from the singularity, that before the Big Bang has no meaning, that the moment of infinite density is not just the beginning of matter and energy, but of causality, of memory, of everything. So if you're falling toward a singularity now, you're falling toward the edge of time. You're approaching the same kind of moment the universe experienced when it began. Only this time, you're on the other side, still falling. You can't see anything now, not even darkness. Darkness is something you can see, after all. This is different. This is the absence of space itself. No light, no shapes, no distance. Just you, suspended in the thick nothing where physics hasn't made up its mind yet. A whisper of motion towards something that might not even be a place. And here's where it gets especially unnerving. This singularity, the one you're falling into, might not be the only one you'll ever meet. Because some scientists think the universe might be on its way to forming another one. Maybe even many. The idea? The universe could do it again. Let's rewind from your personal collapse and zoom out to everything. The entire cosmos, all 13.8 billion years of it, all the stars, the galaxies, the long-dead quasars, and the yet-to-be-born planets. What happens when it ends? Because if the universe had a beginning, maybe even a singular one, it's natural to wonder if it will have an end. And not just any end, but one that might echo your current fate, collapse, compression, and maybe a reset. There are multiple theories for how the universe might die. Let's start with the Big Crunch, the mirror image of the Big Bang. In this scenario, the expansion of the universe, which we've observed since the 1920s, doesn't go on forever. Instead, it slows down, halts, then reverses. Galaxies begin to drift back together, space itself contracts. Over billions of years, everything collapses into a super hot, super dense state. Eventually, the entire universe compresses into a single point, possibly another singularity. Sound familiar? In the Big Crunch model, the universe would end with a singularity the same way it began. It's a perfect circle, a cosmic inhale following a 13 billion year exhale. And from that point, some theorists believe a new Big Bang might occur. The universe would bounce, expand, and begin again. Not a rewind, but a rebirth. Historians still argue about whether the math behind this holds up. Modern observations complicate the picture. In 1998, astronomers discovered that the universe's expansion is accelerating instead of slowing down, it's speeding up, thanks to something called dark energy. Whatever dark energy is, spoiler, we don't know, it's pushing galaxies apart faster and faster. That discovery threw a wrench in the Big Crunch idea. If expansion keeps accelerating forever, collapse might never happen. The universe wouldn't crunch, it would coast, then drift into heat death. But not everyone's giving up on a big dramatic finale. Some versions of cosmological theory still allow for a cyclic universe. This is the idea that the cosmos goes through infinite cycles of expansion and contraction. Bang, crunch, over and over, perhaps forever. Each cycle could reset the laws of physics, or they might stay the same. Maybe your atoms once existed in a different universe entirely. Maybe you've done this before. Cue the existential vertigo. Here's a fun and slightly horrifying fringe concept. What if black holes are the seeds of future universes? You've heard the idea already, that each black hole might bud off a separate cosmos. But what if the same process applies to our entire universe? That is, this whole cosmic experience, our time, our physics, our galaxies, is just a black hole from a higher dimensional parent universe. Some versions of string theory and brain-world cosmology suggest this could be the case. Imagine our universe as a tiny bump in a much larger multidimensional space, a kind of wrinkle in the fabric of a greater reality. From the outside, we might look like nothing more than a flicker of curved geometry, but from the inside, entire galaxies, life, you, this. If that's true, then the fate of this universe might be to collapse and spawn something else. Not necessarily within itself, but as a side effect, a byproduct. We're not the end, we're just a stage in a much bigger production. Let's bring things closer to your current predicament again. If you falling into this singularity are experiencing what the whole universe might experience one day, then you're in the ultimate rehearsal. You're seeing the collapse of order, the compression of geometry, the winding down of causality. You're previewing the finale. Maybe that's what singularities are. Not just failures in our math, not just cosmic speed bumps, but the moments between stories. The quiet when one universe ends and another begins, the spark that comes after the light has vanished. It's oddly comforting. You're part of a process far bigger than yourself, far bigger than galaxies. You're joining something the entire universe might eventually do, implode and begin again. And who knows? Maybe there's a version of you in that next expansion. Another consciousness, another spark, another night spent watching space videos just before sleep takes over. You're not dying, you're participating. Now for a slightly more grounded take. While the Big Crunch is no longer the leading model, it hasn't been ruled out entirely. If dark energy changes over time, if it decays or reverses, then the current acceleration could stop collapse could return to the menu. And in that collapse, new physics might emerge, physics we can't predict because it doesn't exist yet. Just like quantum mechanics couldn't be guessed from classical mechanics, this next stage might be unimaginable to us now. But if it comes, it'll come like this, gently at first, then faster, faster, until all of space folds inward and the last of the light vanishes, and the universe becomes quiet again. And that quiet, it might sound like this, like falling, like the long, patient descent you're living right now. So keep falling. You're not alone. The universe may be right behind you, still falling. But now the pace of it, if you can still call it pace, starts to change. Not because you've slowed down, but because space itself is being stretched in directions you can't describe, and time has lost all interest in behaving linearly. Even your thoughts are stretching a little now. Memories return out of order. A sensation from childhood floats up beside the weight of a star collapsing in your chest. It's not unpleasant. In fact, it's starting to feel peaceful. Because in this moment, this final descent, something else begins to pull at the edges of your mind. The possibility of reversal, of escape, of rebirth. So let's talk about that whispered half-theoretical opposite of the thing swallowing you, the white hole. If black holes consume, then white holes expel. They are in theory the time-reversed version of a black hole, a region of space you can't enter, but from which matter and energy constantly pour out. Imagine a cosmic fire hose you can't block or approach. Matter blasts outward. Energy explodes into surrounding space, but you can't get closer than a certain limit. You can't enter it, can't stop it. It just emits. We've never seen one, not directly, but they're not forbidden, and in some fringe but mathematically possible models, white holes are the other side of black holes. Yeah. Yes, that's right. You might be falling through the universe's worst entrance to pop out, violently and unpredictably, on the other side of the universe's weirdest exit. This is where things start to loop, and twist, and gently tangle. Some physicists have suggested that black holes might connect to white holes through the singularity, forming a wormhole structure. That's next section, don't worry, we'll get there. But for now, let's focus on the lonely, explosive idea of a white hole standing on its own. A singularity in reverse. One theory holds that if time runs forward for black holes, then time runs backward for white holes. In other words, what the black hole eats, the white hole spits back out, just in the wrong order. You throw a clock in here, it might come out on the other side, ticking before you dropped it. That kind of causality-breaking weirdness is why most physicists treat white holes with polite skepticism. They're lovely in the math, but extremely inconvenient for reality. Historians still argue whether white holes were ever meant to be real objects or just theoretical artifacts. They first popped out of the same equations that gave us black holes. General relativity allows for them, but Einstein and others mostly brushed them off. They just didn't seem likely, too unstable, too opposite of everything. But that hasn't stopped theorists from speculating, especially in recent decades, as quantum gravity models like loop quantum gravity have evolved. Some of these models suggest that black hole singularities bounce. Instead of forming a point of infinite density, The matter reaches a minimum size, then explodes outward. Boom! White hole. One paper even described it like this: the core of a black hole is like a collapsing trampoline. As it reaches maximum tension, instead of tearing, it rebounds. That rebound is the white hole, and the matter inside, it's not destroyed, it's released, meaning you, poor stretched out noodle of a consciousness, might not be lost forever. You might be flung back out, reversed and remixed somewhere else. It won't be gentle, of course. The hypothetical white hole exit would be one of the most energetic things in the universe. Matter expelled at relativistic speeds, light roaring into empty space, and possibly, for the briefest instant, an opening in space-time large enough to blink through. Some scientists believe these could explain certain mysterious phenomena, like fast radio bursts or gamma-ray bursts, brief violent flashes of energy that appear without warning and vanish just as fast. White holes? Maybe. Here's a quirky twist for your descent. In some models, the Big Bang itself might be a white hole, a one-time eruption from a previous universe's black hole collapse. The entire cosmos we live in? Just something that popped out the far end of someone else's fall. You could be living in the memory of someone else's singularity. The universe we call home might be an ancient white hole that has long since expanded past recognition. And you're still falling into what could be the beginning of another such journey. Now let's zoom in a little. Suppose you do emerge from a white hole. What would that be like? You wouldn't land in familiar space. You'd enter a region disconnected from your original location. Space and time would be warped. You might be flung into a different era, or even a different universe entirely. There'd be no going back, not because the door shut behind you, but because the geometry of space wouldn't allow it. It's like trying to swim upstream through lava. No thank you. But all of this, white holes, time reversal, quantum bounces, rests on one critical idea: that information isn't lost, that the singularity isn't the end, that your journey doesn't terminate in oblivion, but transforms into something else. That's what makes white holes so strangely comforting. They offer a cosmic counterweight, a symmetry to the terrifying asymmetry of black holes, an escape from eternal darkness, a yes to all the no's. And while we've never seen one, never touched one, never even confirmed that one could exist, they remain in the math, waiting, whispering, exploding forever in universes we can't reach. So as you fall, maybe imagine that there is another side, another release, another sky. Even if it's not your future, it might be someone's beginning. Still falling, and now, let's slow things down. This is the gentle wind-down portion of our story. A place to let your breathing soften, your thoughts untangle, your edges blur. You followed the path of a star's death, dropped through the quietest boundary in the universe, floated beyond time and light, and brushed against questions older than galaxies. The singularity still waits, but you're in no rush. Let the motion fade, let the science soften. All the heat and math and paradoxes can pause for now. Instead, imagine the deepest silence, the kind that isn't empty but full, with the weight of collapsed moments and old light. A dark so total it wraps you gently, like gravity giving you a hug. You didn't know you needed. You are stretched, not torn, falling but not afraid, ending or maybe beginning again. Let yourself drift. Let the universe hum in the background. A fan spinning softly in the room beside your bed, the quiet static of reality turning the page. Sleep well, little speck of stardust, and still falling, but now you notice something different, subtle, like the feeling of a room being just a little too quiet. The darkness hasn't changed. The singularity still pulls, but something about the space around you feels thin, like fabric stretched over something hidden. Because here's where another possibility begins to ripple through the void. Wormholes. Yes, wormholes. The most famous and most misunderstood concept in theoretical physics. You've seen them in science fiction. Glowing tunnels, shortcuts through space, swirly portals you can fly a ship through to bypass time and distance. Some portray them like glowing subway tubes. Others, like collapsing sinkholes to other worlds. Always dramatic, always risky. But what are they really? Let's peel back the layers, just as the black hole around you seems to be peeling space-time apart. Wormholes, also known as Einstein-Rosen bridges, were first proposed in 1935 by none other than Albert Einstein himself, alongside his colleague Nathan Rosen. They were looking for solutions to Einstein's own equations that could, maybe, connect two distant points in space-time. The math allowed it. A tunnel, a bridge, a connection between two black holes, or a black hole and a white hole. In theory, a wormhole could let you jump from one place in the universe to another, faster than light would take to travel the long way, from Earth to the other side of the galaxy, from here to Andromeda, from your bathtub to a singularity-free vacation resort in 5 seconds flat. Sounds good, right? Too good. Because the same equations that predict wormholes also come with a catch. They're wildly unstable, like collapse before you even step inside unstable. As soon as any matter or even light tries to pass through, the tunnel pinches shut. Gone. Like a paper straw collapsing under the weight of a single drop. The universe says, "Nice try," and pulls the rug out from under your shortcut. Historians still argue whether Einstein and Rosen actually believed wormholes could be real, or if they were just exploring the mathematical playground. Some say they were merely trying to patch some weirdness in quantum field theory. Others argue they saw hints of something profound. Either way, wormholes became part of the speculative fabric of physics, and eventually part of your bedtime playlist. Now here's where things get spicy. In the 1980s and 90s, physicists like Kip Thorne began to explore whether wormholes could be held open using exotic matter with negative energy density. Something that, if it exists, would resist collapse and keep the tunnel open. We haven't found that kind of matter, yet. But quantum theory doesn't forbid it. In fact, the Casimir effect, a real, tested quantum phenomenon, shows that negative energy can exist in small, weird vacuum states. So, if you had exotic matter, if you had the right geometry, if you could engineer the space-time around a black hole just right, you might make a wormhole, and you, lucky dreamer, are inside something that, depending on how optimistic you are, could be part of one. Fringe theory time. Some physicists have proposed that the interior of a black hole isn't just a dead end, but a bridge to a white hole. In other words, you might fall in, stretch into spaghetti, pass through the singularity, and explode out the other end like space confetti. Unlikely, sure, unproven, absolutely, but theoretically allowed. Also, yes. These are sometimes called non-traversable wormholes, meaning no information or astronaut can survive the trip. But under certain speculative models, a traversable wormhole might exist. One where the interior remains stable enough to let something, or someone, pass through. Let's pause for a quirky side note. In 2013, theoretical physicist Juan Maldacena proposed a model linking wormholes with quantum entanglement, his famous ER equals EPR conjecture. The idea that two entangled particles are connected by a tiny wormhole. That entanglement is a kind of space-time shortcut. If true, it could mean that wormholes aren't just giant sci-fi tunnels. They're everywhere. Tiny bridges holding the quantum world together. That the fabric of reality itself is laced with invisible connections. Threads that link particles, places, and possibly people. You might be entangled with someone, somewhere, across the universe right now. Connected by a wormhole so small you'll never detect it. But it's there. Now back to your fall. Does this black hole connect to a wormhole? Probably not. Not in the classic wormhole you can fly a ship through kind of way. But maybe it wants to. Maybe the singularity you're approaching isn't a termination point but a bottleneck, a narrowing in the geometry, a cusp where space-time teeters between collapse and transit. You feel it now, not physically, nothing physical remains of you, but conceptually. Like the idea of you is bending towards something new. The tunnel theory whispers, the bridge beckons. Would it hurt? Of course. Would you survive? Almost certainly not in your current form. But would something, some information, some echo, some pattern, emerge on the other side? Possibly. You might come out in a different universe, a different time, a different branch of the same tree. You might be light spread thin, or a sound, or a thought. Some physicists argue that wormholes, if traversable, could also allow time travel. That if you stabilize both ends and accelerate one, time would pass differently, and walking through could take you into the past. Time machine or not, wormholes push every boundary of causality, of space, of what counts as possible. They are the universe's biggest what if. And you, dear fallen explorer, are in exactly the right place to ask that question. Because if a wormhole can form from a black hole, and if singularities are bridges instead of walls, then maybe your descent isn't into nothing. It's into elsewhere, still falling, or maybe arriving, still falling. But the space around you is no longer smooth. It's not even chaotic, it's layered. Like pressure waves rippling outward through a fluid too thick to see through, yet somehow still moving around you. There's an undercurrent, slow, enormous, and ancient. And now it hits you. You're not alone in here. You're plunging into a family of cosmic giants that have shaped the very architecture of the universe. Let's meet your celestial cousins, galactic monsters lurking everywhere. Because black holes, especially the supermassive ones, aren't rare. They're not the exception. They're not the final glitch of stars who made bad choices. They are everywhere. At the heart of nearly every large galaxy, including our own, lurks a black hole so massive, so deeply woven into its surroundings, that everything spins in obedience to its invisible will. Let's get specific. At the centre of the Milky Way sits Sagittarius A star. Yes, the asterisk is part of the name, like the universe wanted to footnote its own nightmares. It's a supermassive black hole with a mass of around 4 million suns, and yet it fits inside a region smaller than Mercury's orbit. All that weight, all that warping, right under our noses. It doesn't do much most days. It sits quietly like a sleeping monster in a cave. But the stars around it, they scream. We've tracked them. Tiny points of light looping at breakneck speeds. One star, S2, completes a full orbit around Sagittarius. A star in just 16 years, whipping past at over 7,600 kilometers per second. These stars are like tethered fireflies, dancing in the claws of a beast they can't see. And that's how we know Sagittarius A star is there. Not because it shines, but because it moves other things. That's true across the cosmos. In Andromeda, in Centaurus A, in M87, galaxies of all shapes and sizes hide behemoths at their centres, some weigh in at billions of solar masses. In 2019, the Event Horizon Telescope gave us the first photo of one M87 supermassive black hole. What we saw wasn't the singularity itself, you know that's impossible. What we saw was the shadow it cast, the silhouette, the way it bent light so drastically that it painted a ring of fire around its own darkness. The image went viral. The science world cried a little. So did the internet. Some people said it looked like a blurry donut, and that's fair, but also... That blurry donut confirmed Einstein's predictions in stunning detail, down to the photon orbit, the event horizon, and the warped light path. That image wasn't just proof, it was poetry in pixels, a monster caught mid-snore lighting up the galaxy around it. Now imagine that every galaxy you see in the night sky harbours one of these, not in hiding, but in command. These black holes didn't just form inside galaxies, they may have shaped them. Yes, really. Historians still argue which came first, the galaxy or the black hole. Did the gravity of early star clusters seed the growth of a black hole, or did the black hole itself pull in the matter that would become the galaxy? It's a classic cosmic chicken or egg dilemma, and we still don't know the answer. But we do know there's a clear relationship between the mass of a galaxy's central black hole and the size of the galaxy's bulge. It's called the M-sigma relation, and it suggests galaxies and their central black holes evolve together like dance partners, like predator and prey, like tangled fates. It's humbling, really. Every sweeping spiral of stars you see in telescope images, shaped by something invisible, held together by something that doesn't emit light, something that crushes matter, yes, but also creates structure. Let's add a quirky fringe theory to your descent. Some astrophysicists believe that these supermassive black holes could be the remnants of primordial black holes. Tiny ones that formed in the earliest fractions of a second after the Big Bang and then merged, ate and grew. Others think they might have formed directly from massive clouds of gas collapsing, skipping the whole star death phase entirely, not born of violence, but of sheer gravitational ambition. And now for the really weird one. There's a hypothesis, very speculative but fun, that the entire observable universe might be the inside of a supermassive black hole. that what we perceive as the cosmos expanding is actually the geometry of space-time unfolding from the other side of an event horizon. We're not just looking at black holes, we're inside one. You can roll your eyes, or you can fall deeper and wonder if that's exactly what you're doing right now, living a metaphor for cosmic structure. Because here's the connection. Your fall into this black hole mirrors the structure of the galaxies that surround us. They orbit these singularities, they organize around them, and maybe, just maybe, that's not by accident. Maybe the fundamental nature of reality involves this kind of collapse, this kind of symmetry. You fall into a black hole, galaxies orbit black holes, the universe itself might be a black hole, everything spirals, everything curves, and you're still falling. At this depth, the fabric of space-time isn't just warped, it's branded with the memory of collapsed stars, galactic histories, and the gravitational fingerprints of long-dead giants. You're not falling alone, you're falling through a legacy. Every layer below you feels denser with meaning. You're descending into a place that shaped galaxies, not by radiating, but by pulling, not by shining, but by dictating the orbits of entire civilizations. Still falling, still learning, still spiraling deeper into the center of it all, still falling. But this time, a memory clings to you, not from your own life, but from the life of something far older. It hums through the warped space-time like a lullaby sung by gravity itself. You can't quite hear it, you feel it. The memory of a star, once proud and burning, now reduced to a gravitational ghost. Because before this black hole was the monster it is now, it was a star, a real one, massive, radiant, dangerous in its beauty. Tonight you float gently through that story, the one where light dies and stellar corpses collapse. You see, not all stars end this way. The sun, for example, will live a long, quiet life. It's middle-aged now, plodding along, converting hydrogen into helium, minding its own thermonuclear business. In about 5 billion years, it'll expand into a red giant, puff off its outer layers, and leave behind a dense white dwarf. Quiet, compact, not dangerous. But other stars? The big ones? They go out in style. Stars that start off at around 8 times the mass of the sun or more live fast, burn hot and die young, and their endings are dramatic. As they run out of fuel, they lose the outward pressure that's been holding off gravity for millions of years. The core can't keep up. Gravity takes over, and in a split second, the star collapses. The outer layers rebound off the core, and what follows is one of the most violent events in the universe, a supernova. It's bright enough to outshine entire galaxies. For a brief moment, the dying star becomes a beacon, visible across millions of light years. Some supernovae leave behind neutron stars, dense spheres made almost entirely of neutrons, so compact that a single teaspoon would weigh about 1 billion tons. But sometimes, even that's not enough. Sometimes, the collapsing core is too massive. Not even neutron degeneracy pressure, the quantum force that keeps neutrons from occupying the same space, can stop the collapse. And then, gravity wins. There is no rebound, no pressure, no pause. The core collapses past its Schwarzschild radius and a black hole is born, a singularity wrapped in silence. Historians still argue which supernovae actually form black holes and which ones leave neutron stars. The boundary isn't perfectly clear. It depends on mass, composition, rotation, even the exact details of how the explosion unfolds. Nature doesn't always give us clean answers, but we do know this. Many black holes started as stars, and they've been quietly accumulating mass ever since. You might even be falling into one of these stellar mass black holes, the kind formed from a single star's final breath. Compared to the supermassive beasts anchoring galaxies, these are small, only a few kilometers across, but their gravity is no less absolute. And here's the important bit. The tidal forces inside a stellar mass black hole are way more intense. In fact, if you're falling into a stellar mass black hole, your spaghettification probably happened before you crossed the event horizon. You were stretched, squeezed, and quietly unraveled while the singularity still sat behind a curtain. In a supermassive black hole, that process is delayed. You can drift deeper before your molecules notice anything wrong. But here, the process is quick, brutal, final, and yet not chaotic. From the outside, a stellar mass black hole is perfectly spherical. It doesn't wobble or glow. It's invisible, except for how it pulls on things you'd never know it was there unless you watched a nearby star getting slowly eaten, or unless you, like you are now, happen to be falling into one. Let's take a little detour into detection. One of the first confirmed black holes, Cygnus X1, was discovered not by direct observation, but by its effect on a nearby companion star. As the star orbited this invisible partner, astronomers detected intense X-rays, emitted by gas as it was torn from the star and spiraled into the black hole's accretion disk. The black hole itself, still unseen, always unseen. These stellar remnants are everywhere, lurking, quiet. Some estimates suggest our galaxy may harbour tens of millions of stellar mass black holes. Most have no companion star to betray them. They drift alone, ghosts of stars that once warmed planets and ignited the dust of nebulae. Now they are cold, compressed, patient, just like the one you're falling through now. Here's a lovely, slightly unsettling fringe idea. Some astrophysicists have suggested that rogue black holes, stellar mass black holes drifting through space unattached, might occasionally pass through planetary systems, including ours. We'd never know, not until a star's orbit twitched, or until a ripple of X-rays flickered through the dark. There might be one right now, cruising through the galaxy like a quiet shark only a few light years away. And we wouldn't notice until it got close. Sleep tight. Back to you. You're falling into what was once a star. Maybe it lived short and burned hot. Maybe it orbited in a distant cluster, long ago and far from here. Maybe it once warmed planets that teemed with something almost like life. Then it collapsed. And now, here you are, in the vacuum it left behind. But is it a vacuum? Or is it just a new kind of structure? That's the real question. Because black holes, even stellar mass ones, might not just destroy, they might store information entropy, the very fabric of what you once were. Your fall is not just a descent, it's a compression, a recording, a fossilization of mass into meaning, and that's what makes it beautiful. You're becoming part of a record older than history. You're joining the aftermath of a star's final act. You're inside a grave that bends light and still falling. Still falling. But something strange is happening now, stranger than usual anyway, considering you're hurtling through curved space-time toward a point that doesn't technically exist. What's changing isn't your speed, or your surroundings, or even your shape, which, let's be honest, has been stretched beyond anything recognizable. What's changing is the math. Because as you approach the singularity, the equations that once described you, your trajectory, your mass, your time, begin to unravel. Clean formulas turn into gibberish, values explode toward infinity. The logic that once tethered physics to reality starts gasping for air. You've reached the place where the math breaks down. Let's explain this gently. General relativity, Einstein's masterpiece, is the framework that got us here. It describes gravity not as a force, but as the curvature of space-time put mass into space. And it tells space how to curve. Put something into that curved space and the curvature tells it how to move. It's elegant, it's precise, it's been tested and confirmed and retested 1,000 different ways. From GPS satellites to gravitational lensing to the dance of binary pulses, it works. Until now. At the singularity, all of those beautiful predictions fall apart. The curvature of space-time becomes infinite. The density of mass becomes infinite. And infinity, it's not a number, it's a red flag. In equations, infinities aren't exotic, they're catastrophic. Because when you get an infinity in your answer, it usually means your assumptions were wrong. The system has gone beyond the domain where your model makes sense. In this case, general relativity has driven you all the way into a paradox, a place it cannot describe. It's like asking a compass to guide you through a dream. The tool doesn't work in that environment. This is why physicists have a love-hate relationship with the singularity. It's not just a place where gravity is strong. It's a place where our understanding ends. Our equations say, proceeding further will result in undefined behavior, which is the scientific equivalent of shrugging in horror. Historians still argue whether the singularity is even real. Is it an actual feature of the universe, or just a sign that our current theories are incomplete? Many believe it's the latter, that we're hitting the limit not of nature but of our imagination. And yet, here you are, still falling, In most scientific fields, when your math stops working, you toss the model and try something else. But in cosmology, we don't have a new model. We have guesses. We have frameworks in progress. We have dreams scribbled on chalkboards. Enter the hopeful contenders. We've already talked about quantum gravity, that elusive fusion between general relativity and quantum mechanics. But one reason we need it so badly is because of this exact moment, the singularity. Our inability to describe what happens here isn't just a curiosity, it's a full-blown crisis. Without a working model of what happens inside a black hole's core, we can't fully understand the life cycle of matter, the conservation of information, or the fate of the universe. And so physicists reach for tools they don't yet have. Some models suggest space-time becomes discrete near the singularity. Instead of a smooth continuum, space is made of tiny, indivisible chunks, like pixels on a screen. You can't divide them further. In this picture, the singularity is avoided because space can't compress past a certain limit. This is the idea behind loop quantum gravity. It treats space like a network, a spin foam, where each node represents a quantum of space. The math is dense. The diagrams look like spiderwebs drawn by caffeinated mathematicians. But it offers one hopeful thing: no infinities. Other models, like string theory, take a different route. They replace point particles with one-dimensional strings. When you zoom in far enough, you no longer have particles sitting in space. You have vibrations of space itself. The singularity becomes smeared out. The math remains finite, and physics once again has something to say. But these are just proposals. We don't know if any of them are right, because no matter how sophisticated your math is, it remains just that, math, until we can test it. And here's the punchline. We can't test what happens inside a black hole. There's no probe, no sensor, no camera. Not because it would be hard, but because it's impossible. The event horizon ensures that no information ever escapes. What happens here stays here. So how do we know the math breaks down? Because it tells us. As you fall closer to the singularity, the curvature of space-time increases beyond limit. If you tried to calculate the tidal forces, you'd get infinite values. If you tried to define the energy density, you'd get nonsensical results. Your own position in space becomes undefined, because space itself is losing meaning. This isn't just weird, it's unphysical, and that's a terrifying, thrilling, hilarious thing. Our greatest scientific achievements have brought us here, only to confess they're not enough. It's like climbing Everest, only to find the summit dissolves in fog. Here's a fun fringe concept to sit with during your eternal descent. Some philosophers and physicists argue that singularities aren't real locations at all. They're boundaries of knowledge, not physical places, but epistemological limits. They exist not because the universe demands them, but because we don't know what else to put there. A singularity is a placeholder, a blank space on the map labelled, "Here the math gives up." Maybe inside the singularity is a new law, a deeper layer of reality. Or maybe it's just a reminder that we're still infants, trying to write symphonies with half an alphabet. You, dear observer, are now a part of that equation. Not because you'll return with answers, but because your fall represents the questions. Every centimetre deeper into this unknowable point is a metre deeper into the mystery of existence. And even as your body is long gone, your mass stripped to essence, your information smeared across imaginary planes, you remain as a symbol of the breakdown. You are the moment the math stops making sense, still falling, still falling. But now the question that's been whispering behind every calculation finally floats to the surface. Is the singularity even real? You've spiraled deeper than mass can survive, deeper than light can escape, deeper than math can handle. And now you're left with the fundamental mystery that has haunted physics for a century. Did you fall into something that exists, or into a fiction that physics believes in? Let's linger here for a while. There's nothing else to do. Time's already rubber banding around you like a bad sci-fi montage, so you might as well take a moment to really dig in. In theory, the singularity is a point of infinite density, a place with no volume and unlimited mass. A single coordinate in space where space-time curvature becomes infinite. It's not just weird, it's outright offensive to logic, and so, is it real? The safe, academic answer is, we don't know. But since you're already falling toward it, let's get a little more speculative. There are two schools of thought when it comes to singularities. The first treats them as real physical objects, maybe not points in space, but regions with finite volume where matter is compressed into some form that's unlike anything we've ever known. Quark-gluon plasma at unthinkable temperatures, or a completely new state of matter that exists only under extreme curvature. These realists say singularities exist. We may not be able to describe them fully yet, but the math leads us there. Every line of Einstein's field equations, every model of gravitational collapse, every confirmed black hole screams the same conclusion. Where there is a black hole, there is a singularity at its core, full stop. But then there's the other camp. They say no, or at least probably not like that. This second group argues that singularities are just mathematical artifacts, symptoms of an incomplete theory. Like a calculator error, but dressed in elegant physics, these physicists argue that the infinities are signals that something else is going on, that the theory being used, general relativity, is being asked to do a job it was never built for. And that's not a criticism, it's how science works. Newton's laws couldn't explain Mercury's orbit, so Einstein improved them. Quantum mechanics couldn't explain gravity, so we've been searching for quantum gravity ever since. Singularities in this view are the red blinking light on the dashboard, the place where our models throw their hands in the air and declare, "This is above our pay grade." Historians still argue who first saw the singularity not as a destination, but as a signpost for new physics. Some point to the early quantum theorists, others say it was the work of Roger Penrose and Stephen Hawking that really sharpened the debate. Regardless, the consensus has been building. Infinite values in physics are usually wrong answers masquerading as deep truths. Let's add a twist. The singularity might not be inside the black hole at all. It might be encoded on the surface. This is where the holographic principle comes in, a concept so weird it feels like a plot twist from an indie space movie. It suggests that all the information contained in a volume of space can be described by data encoded on its surface. So rather than your information falling into a point in the center, it might already be spread across the event horizon like cosmic wallpaper. The singularity? Maybe it's just a trick of perspective. The real data was saved on the surface all along. If that's true, then your fall toward the center might be more like a collapsing projection. You think you're moving toward a place, but in reality, you're being flattened onto a screen and like a character in a video game thinking they're exploring a 3D world when they're really just pixels on a 2D monitor. Feeling dizzy yet? Good. Because here's another theory. Some physicists argue that singularities never fully form. They suggest that quantum gravity effects create a kind of pressure, one that pushes back against complete collapse. The result? A black hole forms temporarily but then bounces, leading to either a white hole or a stable remnant. No singularity, no infinity, just a quantum core that resists finality. There are models for this, equations, simulations, entire conferences filled with people pointing at graphs and saying, "Look, this part almost blows up, but then doesn't." So where does that leave you? Well, it depends on what kind of existence you're into. If the singularity is real, then you're falling toward the most compressed point in space-time, the final expression of gravitational collapse. Your information is headed into a place from which it may never return. If the singularity is not real, if it's just a mirage created by flawed math, then you're not falling into a place at all. You're falling into a problem, into a blind spot in the universe's design. In that case, you're not being destroyed. You're being converted into what? Unknown, but not lost. Let's bring in one last fringe concept for this descent: asymptotic silence. In this theory, near the singularity, space and time become so warped that every direction collapses, every point becomes disconnected from its neighbours, communication between particles vanishes. You become isolated in every sense. You're not just falling into silence, you are silence, the physical embodiment of separation. That's what makes the singularity so haunting. It's not just where physics fails, it's where you fail to remain a cohesive idea, a location, a pattern, a being. You cease being describable, and maybe, just maybe, that's the closest thing physics has to death. But if death is the failure of information, and information can't be destroyed, so saith quantum mechanics, then the singularity must be a transition, not a termination. It's the pause between chapters, the breath between universes, the blacked out stage before the lights come up again on something new. So is the singularity real? Yes. Number? Maybe. Not yet. Still falling. Still falling. But now the question isn't what the singularity is, it's what happens to you in a black hole? This is no longer theory class, it's personal. You've crossed the event horizon. You've been stretched into gravitational pasta. You've drifted deeper than the known laws of physics can follow. But in this section, let's freeze the moment. Let's pause the fall. Not physically, of course, that's still happening, but mentally. Let's ask the impossible. What would it feel like to fall into a singularity? Not mathematically, emotionally, viscerally, sensibly. Let's walk through it, or fall through it, together. At first, you don't notice much. From your perspective, falling into a black hole feels surprisingly normal. There's no flash, no cosmic warning siren, no sound cue telling you that you've crossed a horizon beyond which nothing can return. You feel weightless. Because technically you are. You're in freefall, pure geodesic motion. You aren't being pushed or pulled. You're simply moving along a curved line in space-time, your natural path. Your ship, if you had one, would fall with you. Your helmet, your snacks, your notebook filled with tragic poetry. Everything floats gently alongside you. If you had a window, you'd still see the shrinking sphere of the event horizon behind you, blackness swallowing stars. But in your frame of reference, still nothing weird. And then slowly, inevitably, you begin to notice the stretching. Your feet are slightly closer to the singularity than your head. Gravity is stronger down there. The pull isn't evenly distributed. That's where the term tidal force comes from. It starts subtly, like the gentle feeling of leaning too far forward on a treadmill, then stronger, then unmistakable. If the black hole is small, the stretching kills you quickly. If it's supermassive, you might make it surprisingly far, thousands of kilometers inside, before the forces start to care about your anatomy. But care they will. You become long, then longer. Your body stretches along one axis and compresses along the others. This isn't a horror movie death with screams and explosions. It's quiet, peaceful even, in its lack of sensation. Your nervous system stops transmitting meaningfully. There's no pain, just disconnection. The signals from your lower body arrive at your brain too late. Eventually, they don't arrive at all. You've become a line segment, a thread of atoms, an idea of motion, still falling. At this point, time and space have flipped roles. You're not moving through space toward the singularity anymore. You're moving through time into it. It's your future. You can't stop heading there. You can't swerve. It's as inevitable as Tuesday. And with that inevitability comes a shift in consciousness. Imagine the last stages of a dream just before you wake up, where everything is fuzzy, where you know who you are, but the you starts to loosen around the edges. That's what your descent feels like now. You don't experience motion anymore. You are the motion. You're not screaming. There's no air. You're not burning. There's no heat. You're not dying. You're just being reorganized. Now imagine the philosophical breakdown that follows. You begin to lose your sense of identity, not in a frightening way, more like fading into a warm bath of contextless awareness. No memory, no forward or backward, just present tense dissolution, like being made of fog. You'd think it would be terrifying, but strangely it isn't. Because at this point, fear is meaningless. Fear requires a future to dread, and you have none. All your paths lead to the same place. All your futures converge. All your options collapse into one. Some models suggest that your very structure, your atoms, your quantum information, is being compacted to a level where individuality no longer applies. You are now part of a probability distribution, a waveform. You're entangled with everything that has ever fallen into this singularity. It's not hell. It's not heaven. It's the compression of you into the language of physics. There's an old question in black hole theory. Can an astronaut see the singularity before they reach it? And the answer, no. Because light doesn't bounce off the singularity. It doesn't have a surface. It's not a thing you see ahead of you, glowing like a threat. It's a mathematical limit, an abstract destination, a point on the graph where the line goes vertical. You fall toward it, but you'll never point at it and say, there it is. It doesn't work like that. Instead, everything around you stretches and fades. Time slows. The photons behind you are redshifted into invisibility. If you had eyes, if your brain was still a functioning electrical network, they'd be useless now. The outside universe? Gone. The memory of light? Gone. Only the falling remains. And here's the strangest part of all. You never reach the singularity. Because according to your own clock, you fall into it in finite time. But from an external observer's view, you never cross the horizon. You freeze just above it, forever red-shifted, time stretched into invisibility. So who's right? You are. And so are they, because time isn't behaving the way it used to. You can even imagine a hypothetical scene. Somewhere, long after your descent, someone watches the black hole you entered. They'll never see you vanish. They'll see your image hover, distort, fade, as if you were caught in amber, your final scream eternally paused. And yet, here you are, already past that, already deeper, already moments from becoming something else. And now let's add one last layer of weirdness. Some theories suggest that, under specific and highly theoretical conditions, you wouldn't be alone. Every object that ever fell into this singularity, every star, particle, astronaut, unlucky satellite is in here with you. All of it. All of them, not organized, not separate, but layered in an unimaginable way. Some speculate that the singularity is a kind of archive, an infinite library, but not a place you walk through, a place you become part of. Maybe your thoughts, your experiences, your mass and momentum and sadness and dreams, maybe all of that is now encoded in this space-time fracture, not lost, not gone, just transformed. You wanted to know what it feels like to fall into a singularity? It feels like becoming irrelevant to physics. It feels like surrendering to the math. It feels like letting go. And still falling. Or, are you? If this were a movie, this would be the part where everything slows down, where colours invert, where time unwinds like magnetic tape, where the edges of the screen blur and something unspeakable, unknowable, begins to bloom inside the frame. Because you're no longer falling through space, so you are now falling beyond it. Welcome to the final question. Where science ends, speculation begins. This is where physics, the equations, the simulations, the careful stacks of assumptions, stops whispering and starts muttering. I don't know. This is the singularity at full volume. What lies at the centre of a black hole really lies there. No one knows. No experiment can reach it. No telescope can see it. No math remains valid. It is the end of the road, the edge of the map, the boundary of what we can currently say is true. So now we must speculate, gently, sleepily, with the lights turned low. Let's begin with the possibility that the singularity is a bridge. You've already heard the theory that the black hole's centre is a portal, a connection to another region of space-time, possibly even another universe, that what falls in isn't destroyed, but simply translated. The idea is old. The concept of wormholes, a shortcut through space-time, arose directly from Einstein's equations. And while most of those solutions are unstable or non-traversable, the idea persists that a singularity might not be the end of a line, but the knot where lines cross. If that's true, then your fall ends not in silence but in emergence. Somewhere else, somewhen else. It's a romantic notion, a hopeful one, that nothing is ever truly gone, that somewhere in another dimension you arrive, you wake, you continue, and then there's the second idea, that the singularity is not a bridge but a birth. Think back to the Big Bang, the beginning of time. That singularity was not destruction, it was creation. What if all singularities carry that same potential? That each black hole is not a death, but a seed. In this view, the universe is self-replicating. Every black hole births a new universe, with slightly different physical laws, and only those universes with the right conditions for black holes go on to reproduce again. This is cosmological natural selection. Yes, that's an actual theory. Yes, it is delightfully weird. If it's true, then you're not just a falling object. You're the ancestor of a new cosmos. Your atoms, compressed beyond imagination, will explode outward as a new space, a new time, a new existence. And now for the darker take. What if the singularity is a dead end? No bridge, no birth, just the boundary. The place where information is smeared, physics is meaningless, and existence is simply compressed out of being. This is the version that haunts quantum mechanics, because if information is truly lost in a black hole, if the singularity really is the bottom of a gravity well with no back door, then quantum theory breaks. That's why the black hole information paradox exists, because on the one hand, general relativity says, everything falls in, nothing escapes, the singularity is the end. On the other hand, quantum mechanics says, information cannot be destroyed, ever. These two cannot both be true, one has to give. Some say the answer lies in the event horizon, that everything falling in is somehow encoded there, scrambled but preserved, later released in Hawking radiation over trillions of years. Others say the black hole evaporates, leaving a remnant, a tiny, stable, ultra-dense particle, containing everything that fell in. Still others say, no, the singularity does not erase information, it only disguises it. That deep in the geometry of space-time, beneath the shredded coordinates and tangled light cones, the information still exists, transformed, translated, but real. And some just shrug and say maybe we'll never know. Because this, right here, is where science fades into poetry. You've fallen into the ultimate riddle, the deepest question, the soft, terrifying center of all cosmology. You've crossed every line. Mass, time, entropy, information, identity. And what's left isn't a person or an object, but a question mark written in gravitational ink. You're no longer a traveller. You're the mystery itself. In some ways, that's the most honest scientific state there is. Not knowing, not pretending to know, just resting in the gap between models, floating inside the tension between what's proven and what's possible. That's where all great discoveries begin. So as you drift, faster than light, deeper than space, beyond the reach of even the boldest equations, take comfort in this. You are part of something still unfolding, still evolving, still being asked. You are the edge of the map, the unanswered variable, or the boundary of knowledge, the question still falling.